From the desk of K3MT in beautiful downtown Culpeper, Virginia, it's a video instruction. To protect the intellectual property wrung from weeks of work, this presentation is copyrighted. Send comments, corrections, or correspondence to K3MT at arrl.net. This instruction is a sequence of comments on VariCode, a variable length digital coding system, and it shows some applications. The scope of this presentation is binary two-state serial codes with uniform length on-off intervals. These are the bits. The bits are constant in length. Codes can be bit synchronous that have uniform on-off or marked space-time intervals, or they can be asynchronous, in which the symbols themselves are bit synchronous, but there can be a variable length idle state between symbols, allowing for variable timing. There are four common examples of these binary two-state codes. Two of the early ones are Morse, which go back to the about mid-1800s, and BAUDOT, which came about sometime about 1925 or 30 time frame prior to World War II. The other two more modern examples are ASCII, American Standard Code for Information Interchange, and PSK31. PSK31 is a modern example of a varicode, and Morse is an early example of such a varicode. At this time, I'll dispense with the waveform state showing the lines between 0 and 1, and instead show the symbols 1 for a high-level state, 0 for a low-level state, as is commonly done. The timing between sequences of 1s and 0s is shown as a dotted line, which indicates that the circuit can be idle, that is, transmitting zeros, for an indefinite length of time. In asynchronous systems, this is commonly done. The bit patterns for Morse, letters A and B, are shown in the first line below, BAUDOT, A and B in the second line, ASCII in the third line, and PSK31 on the fourth line below, as an example. Let's look at fixed-length codes. Initially, the circuit is idle, transmitting a sequence of zeros. Then, there must be a transition to 1 to start things, and this transition, shown in green here, is called a start pulse. After that, there can be combinations of 1s or 0s, 5 in BAUDOT or 8 in ASCII, and that sequence must be followed by a return to the idle state, which is 2-bit zeros in ASCII, and a shortened 2-bit 0 in BAUDOT, 1.42 units long. After this, the next start pulse can occur, or the circuit can go idle. In synchronous mode, the start and stop pulses may be omitted, but this requires a very accurate clock and timekeeping at both ends of the link. In variable length codes, the situation is similar. The circuit is idle, transmitting a string of zeros, and things must start with a transition to 1. However, unlike BAUDOT with its 5 units following the 1, or 8 units in ASCII following the 1, the symbol can be of any length desired. So there need to be some sort of means of saying when it is over, and that means is to put 2-bit zeros at the end of every symbol. So the symbol can start with a 1, have any number of 1s and 0s that you wish, but if a 0 appears, it cannot be followed by another 0, or that would signify the end of the symbol. Zeros must be followed by a 1, but there may be as many 1s in a row as is desired. Well, what is the use of varicode? Think of normal English text. The E occurs about 11.5% of the time. 8.5% of the characters in text are A, then in order follow I, R, T, O, N, J and Q appear about once in 500 characters. In ASCII use in your computer, each letter takes 8 bits. Morse, on the other hand, is a varicode. The E, a single dit, as it will turn out, and we will see later, is 4 bits long, and the letter Q, which is da, da, dit, da, as shown here, is 18 bits long, and the E occurs more frequently than the Q, so Morse is a varicode. There is an excerpt here from 11, a short essay, with the E's nicely outlined in red, and if you notice, the J and Q never appear in this sequence. But there are a lot of E's. Well then, how about a drawing? A drawing is a group of black lines or some constant color line on some constant color paper, often white. If I were to break this into pixels and try to transmit it, it would make perfect sense to use the shortest possible symbol for the paper background color, the most commonly occurring pixel, and a short symbol for the black pixels along the lines. If the drawing had other colors in it, it would make sense to sort out the pixels of different colors and how many there are of each, and assign the codes in increasing complexity accordingly. Yet longer codes for text or less used features could be applied to the drawing, and in this way save transmission. With this in mind, let's take a look at how we would build a varicode. Recall that it begins with an idle circuit transmitting zeros, and things start when the first 1 appears. The first 1 could in fact be the simplest symbol. It must be followed by 2 zeros. Now every symbol is followed by 2 zeros, so here I will delete the double zero end of the symbol. To make a second symbol, what I need to do is just simply take the first symbol and prefix it with a 1 to get 1, 1. Then I can get a new symbol by prefixing the 2-bit symbol with a 1 to get 1, 1, 1, and prefixing the symbol of 2 less bits, the 1, with a 1, 0. So I can get 2 new symbols, 1, 1, 1, 1, 0, 1. And I can continue this in like manner by prefixing the symbol 1 bit less in length with a 1, and the symbol 2 bits less in length with a 1, 0. So I have 1 symbol with a single bit, 1 symbol with 2 bits, 2 symbols with 3 bits, 3 symbols with 4 bits, 5 with 5 bits, 8 with 6 bits, and so on. And I can continue this as far as I desire. An interesting property pops up at this time. Again, I ignore the double zero symbol stop state. So I have only 1 symbol 1 bit long and 1 2 bits long. Each of these spawns 1 other symbol, so I get 2 symbols 3 bits long. And the general rule is the number of symbols of n bits is equal to the number of symbols of n minus 1 bits plus the number of symbols of n minus 2 bits. That is, the number of symbols of 3 bits is equal to the number of symbols with 2 bits plus the number of symbols of 1 bit. This is an interesting sequence. The sequence is 1, 1, 2, 3, 5, 8, 13, 21, 34, and on. This is known in mathematics as a Fibonacci series, F11. In a Fibonacci series or Fibonacci sequence, each member of the sequence is the sum of the previous 2. In other words, if you started with 2 numbers A and B, the first 2 members would be A and B. The third member would be the sum of the first 2, A plus B. And the next member will be the sum of the previous 2, B plus A plus B, and so on and so on. Another useful property pops up. Besides the short sequences for the most frequently occurring symbols, the varicodes are open-ended. BAUDOT is a fixed-length 5-bit code encode only 32 symbols, which are the 26 letters, and space, line feed, carriage return, null or rub out, figures, which is shift to uppercase, or letters to shift to lowercase. ASCII is a 7-bit code. It can encode 128 symbols. That'll give you the upper, lowercase letters, numbers, punctuations, etc. The 8th bit of ASCII is unassigned and can have different meanings. Varicode, on the other end, is open-ended. There's an unlimited symbol set, although the length of the symbols grows as we add more and more symbols to our entire alphabet. The two common varicodes in use today are PSK31, which follows the earlier development. The number of symbols of a given length follows the Fibonacci sequence, as we had seen before. In PSK31, a single-bit symbol 1 is the spacebar. 11 is the lowercase letter E. 101, the lowercase letter T, and so on. Morse is a different type of varicode. It was really made up as a code of rhythm, and it speaks to people. It's a separate rhythmic language. In Morse, there is a variant. There are two basic elements in Morse called dits and daws, or the uninitiated call them dots and dashes. The timing in Morse is 1 bit long, and it is called a dit space, or a bit. A dit takes 2 bits. You must go on and then off to send a dot or a dit in Morse code, which is a 1-0. A daw takes 4 bits, 4 dit spaces, 3 on, 1 off. Symbol separation between symbols takes 2 additional dit spaces, both 0. And word separation takes 7 total bits. And in fact, the word separation is 2 of the 2 dit space zeros and 1 of 3 dit space. What is shown here is the word test in Morse code. The T is a single daw, 1110. The 2 zeros separated from the E. The E is a dit, 10, and the 2 zeros separated from the S. The S is 3 dits, 10, 10, 10, and there are 2 zeros separating it from the T, and the T again is a daw, 3 ones and a 0, followed by 2 zeros. Then there are 2 zeros following that, and 3 more following that for word space. And that is the structure of Morse. Let me set aside the double zeros and triple zeros necessary to separate symbols one from another and words one from another. To build Morse code, I need to start with a dit and a daw, that is the letter E, the letter T. The E is 2 bits long, 10. The T, as we had seen, is 4 bits long, 1110. I can prefix the E, the 10, with another 10 to get a symbol 1010, the letter I. Now I have one symbol 2 bits long, 2 symbols 4 bits long. I can make symbols 6 bits long with a stratagem of taking a 10 in front of each symbol 4 bits long, and a 1110 in front of the symbol 2 bits long, and I get 3 symbols that are 6 bits long. I can continue this stratagem to make 8-bit symbols simply by prefixing each 6-bit symbol with a 10 and each 4-bit symbol with a 1110 to continue building the code, and then go in like manner to build up all of the characters of Morse code. And as if you will notice, this is a variable length code. Well, interesting. Is this a Fibonacci sequence? There is one symbol 2 bits long. There are 2 symbols 4 bits long. These are the roots of 3 symbols that are 6 bits long. The 2 4-bit and 3 6-bit symbols are roots of 5 symbols 8 bits long, and the pattern continues. This looks like some sort of Fibonacci sequence, but is it really? If I do my book work, I find the number of symbols of length n is as follows. For n equals 2, I have one symbol. For n equals 4, I have 2. N equals 6, I have 3. N equals 8, I have 5. N equals 10, I have 8, and so on. This is a Fibonacci sequence, but the first two members are 1 and 2. So each member of the sequence is the sum of the preceding two. I do 1 and 2. The sum of that is 3. The sum of 2 and 3 is 5, and etc. But this is nothing more than the Fibonacci sequence 1, 1, missing its first term. So indeed, the Fibonacci sequence 1, 1 does appear in Morse code. Morse could be reduced. The standard Morse has a dit 2 bits long and a daw 4 bits long. The daw is on 3 times as long as the dit, a 3-to-1 ratio. In actual timing, it takes 2 dits to a daw. The 2 dits would occur in the same time interval as one daw. Morse is a musical, rhythmic language made for human reception. However, if machines are listening to this, why not reduce the daw to just 3 bits, 2 on, 1 off? This would build a slightly different version of Morse, and we could take the 2-bit zeros and the 3-bit zeros and shorten them as well, and this can be done and is sometimes done. Well then, how could I build a table of symbols of reduced Morse? First, start again with E, the standard Morse 1-0. Prefix it with a single 1 to get a 3-bit symbol, 1-1-0. Then I can prefix the 2-bit symbol with 1-0 to get 4 bits, 1-0-1-0. Having done this, I can put 1-0 in front of the 3-bit symbols and 1-1-0 in front of the 2-bit symbols to get 2 5-bit symbols, and continuing in this pattern. I've shown the table here. You can follow through it if you wish, and you find that the number of bits in a symbol and the number of symbols of that many bits is as follows. 2 bits gives you 1 symbol, 3 bits gives you 1 symbol, 4 bits gives you 1 symbol. 5 yields 2 symbols, 6 yields 2 symbols, 7 yields 3 symbols, 8 yields 4 symbols, 9 yields 5 symbols, 10, 7 symbols, and 11 bits, 9 symbols, and so on. Study the table. You'll see this pattern. Well, is this a Fibonacci sequence? Sort of, but not exactly. Here's the table that we just discussed. If you notice, this is a sequence that begins with 3 terms, 1, 1, and 1. And each further member is a sum of the previous 3 minus the previous 1. Look at the 4th term. It's a 2. It's a sum of the first 3 terms, 1, 1, 1, minus the 3rd term, 1. So in this case, the number of symbols of length n is equal to the number of symbols of length n minus 2 plus the number of symbols of length n minus 3. Sort of a Fibonacci sequence, but a bit different. So what does this all mean? Well, first, Varicode can shorten transmission time for certain messages, such as normal, English, or as it turns out, German or French text. It could shorten the transmission time of line drawings. And Varicode is open-ended. You can generate as many symbols as you may need. It does give rise to Fibonacci and Fibonacci-like sequences, and that is the purpose of my study on this. As I began into this, I found it curious. Fibonacci rides again.